Hello students, welcome to another section of topology. Here we discuss what is a separable space. We have already discussed this concept of separable space in metric spaces, which is same as in the topological space also. A topological space X2 is said to be separable. X2 is said to be separable if it has a countable dense subset. Countable dense subset. So you remember definition of denseness in topological space, and there is a criteria for denseness in topological space that says that A is dense in X if and only if for every non-empty open set B in X, comma, A intersection B not equal to empty. If you want to check a set is dense in the space capital X, we need only check that A intersection B is either empty or non-empty for every open set B in capital X. Okay, so using this idea, we can easily understand what is the concept of denseness. And example for a separable space is you take your real line with the usual topology tau. Then you know Q, the rational numbers, is dense in R and it is countable. So Q is a countable dense subset of real line with the usual topology. Therefore, R with the tau is separable. So separable space are space which have a countable dense subset. Okay. Now, in the last class we have discussed the compactness and nillowness. Okay. And we have told that suppose X2, X1 and X2 are two topological spaces A and A is a subset of X, then if tau1 restricted to A equal to tau2 restricted to A, okay, then we have told that we have discussed that when A is compact with respect to tau1, then A will be compact with respect to tau2 also. A is compact with respect to tau1 implies A is compact with respect to tau2. With respect to tau2 also. So, when these conditions hold, what about the property of denseness? For that I consider an example. Let X be a set with at least 2 points, at least 2 elements. X be a set with at least 2 elements. 2 elements. Okay. Then I take tau1 be the indiscrete topology. I take tau1 equal to tau I indiscrete topology and tau2 equal to tau d, that is discrete. It is indiscrete, here discrete. So X tau1 is a topological space and X tau2 is a topological space. Okay. Now I take capital A equal to the set, some singleton set A, and here you take capital X is equal to some set AB. Okay, X is equal to AB. X tau1 is a topological space, X tau2 is a topological space, and you can easily see that tau1 and tau2 are two different topologies. And now you take A equal to singleton A, then A is a subset of X. Okay. Then what is tau1 restricted to A? Tau1 restricted to A is nothing but set of all subset A intersection G such that G belongs to tau1. So this is the definition of tau1. So which is equal to tau1 restricted to A, which is equal to set of all subsets. What are the elements in tau1? Tau1 is indiscrete topology on capital X. This is capital X. Indiscrete topology means tau1 contains empty set and X itself. And tau2 contains discrete topology, that means empty set X and singleton A, singleton B. This will be the tau2. Then what will be A intersection G, where G belongs to tau1? This is A intersection What are the G's in TOE1? TOE1 has only two elements, empty and A intersection A capital X. This will be TOE1 restricted to A, which is equal to empty set and A itself. This is TOE1 restricted to A. What is TOE2 restricted to A? A intersection open sets in TOE2, empty, A intersection X, A intersection singleton set, comma, A intersection singleton B set. So which is equal to A is singleton A. So empty set A intersection singleton A intersection X means singleton A. Okay, that means A itself, and A intersection A is A itself, and A intersection B is A is singleton A, B is singleton B. Okay, then A intersection singleton B is again empty, and empty is here, so I take the empty set and singleton A itself. Okay, so these are the two sets, and this is nothing but empty and A. Okay, so you get TOE2 restricted to A is empty set and A, TOE1 restricted to A is empty set and A. So here TOE1 restricted to A and TOE2 restricted to A are equal, same, but remember TOE1 and TOE2 are two different topologies on X. Okay, now what happened to the denseness of A in TOE1 as well as in TOE2? So how will you find A is either dense in X or not? A is said to be dense in X. A is said to be dense in X by the definition if A closure equal to X. This is the definition of dense set. Now you consider what is A closure with respect to TOE1. What is a closure of a set? Closure of a set is the smallest closed set containing A. By definition, it is smallest closed set containing A. A ne contain ചെയ്യുന്ന ഏറ്റവും ചെറിയ closed set ആണ് A closure. Okay. So what are the closed sets in TOE1 which contains capital A? So what is TOE1? TOE1 is empty set and capital X. So what is the closed sets in TOE1? It is again capital X and empty set. They are complements. So you know what are the closed sets? Closed sets in TOE1 are complements of the elements TOE1. In TOE1 are again empty set and capital X, and closed sets in TOE2 are their complements capital X, empty set, singleton B and singleton A. Okay, so these are the closed sets in TOE2. Ready? Now you need to find A closure with respect to TOE1. That means the smallest closed set containing A. Here there is only two closed sets, empty set and whole set. So the smallest closed set containing A is nothing but X. Therefore A closure with respect to TOE1 is capital X. What happened A closure with respect to TOE2? What are the closed sets containing A? A means singleton A. So the closed sets containing A, the element A is nothing but X and singleton set A itself. So these are the two closed sets containing A. Okay, then what is its closure? Closure is the smallest closed set. So a capital X is a full set and therefore A will be the smallest one. So A closure with respect to TOE2 is A itself. Ready? So what you can say now? A closure with respect to TOE1 is equal to X. That means it satisfies the definition of dense set. When A is dense in X, A closure will be equal to X with respect to the corresponding topology of X. So I can say that A is dense in X with respect to TOE1. That means when you consider X TOE1 as a topological space, then A equal to singleton set A is a dense subset of X. But A is not dense in X with respect to, when you consider it as a X TOE2 discrete space, it is not dense in X. It is just a closed set because its closure equal to A. So what I would like to conclude at that, if TOE1 restricted to A equal to TOE2 restricted to A, even though these two topologies are coincide and A is dense in X with respect to TOE1, doesn't implies A is dense in X with respect to tau 2. So the property which is hold for compactness doesn't hold for denseness. അല്ലേ, ഇതേ കാര്യങ്ങൾ തന്നെയാണ് നമ്മൾ കോമ്പാക്ട്നെസ്സിൽ ഡിസ്കസ് ചെയ്തത്. പക്ഷെ അവിടെ ടോവണിൽ കോമ്പാക്റ്റ് ഉണ്ട്, രണ്ടുപേരും റെസ്ട്രിക്ട് ചെയ്യുന്ന ടോപ്പോളജി അതേ സെറ്റിൽ സെയിം ആണെങ്കിൽ കോമ്പാക്ട്നെസ് ഒന്നിലുണ്ടെങ്കിൽ രണ്ടാമത്തേലും ഉണ്ട് നമ്മൾ പറഞ്ഞു. പക്ഷെ ഡെൻസ്നെസ്സിൻ്റെ കാര്യത്തിൽ വരുമ്പോൾ നമുക്കത് കൺഫേം ചെയ്യാനായിട്ട് പറ്റുന്നില്ല. ഓക്കെ, now let's see what are the relationship between Lindelofness, compactness, second countability and separability, etc. So first we have a theorem, every second countable space is Lindelof. That means second countability always implies Lindelofness. And this is a trivial theorem. Actually in the section of second countability, earlier section in the topological space, you proved a theorem that states that when a space is second countable, then every open cover of that space will have a countable subcover. Now you have the definition of Lindelofness. Every open cover of X has a countable subcover, means that space is Lindelof. So which together form this theorem applicable. So I take let X tau be a second countable space, and by previous theorem, not actually by earlier theorem, comma, every open cover of X has countable subcover, which means capital X tau is Lindelof. So actually we need to write the proof of this theorem here, but I am skipping this proof here. Now we have one more theorem, every second countable space is separable. How will you prove that every second countable space is separable? That means second countability, not the countability, second countability. Second countable means it has a countable base. Second countability always implies separability. So second countability always implies separability. This is we need to prove. So for the proof, let X tau be second countable. Second countable means it has a countable base. Then it has a countable base B. Then it has a countable base B. We need to prove that X is separable. How will we prove? We have to prove that capital X is separable. That means it has a countable dense subset. That is, X has a countable dense subset. So we know X has a countable base B. Okay. When B is a base for the topological space X tau, clearly B will be a subset of X, right? We have B be a subset of X. Therefore we claim that B itself is a dense subset. B is dense in capital X. B is dense in capital X. So how will you prove that a set is dense in capital X? How will you prove that a set is dense in capital X? Intersection with any open set is non-empty. Okay. So let A be non-empty open set in capital X. Okay. Then since A is an open set, A belongs to corresponding topology tau. Then since B is a base for tau, every members in the topology can be written as union of elements of B. Therefore by definition A can be written union of some members of B, which implies A intersection B will be non-empty, because A is nothing but union of some members of B. Therefore A will intersect with B. Therefore their intersection is non-empty, which implies since A is any arbitrary open set, B will be intersect with any arbitrary open set of capital X, which implies B is dense in X. And we already know B is a countable base, therefore B is a countable set, which implies B is a countable dense subset of capital X, which implies capital X is separable.